Hi everyone, my name is Salma Tawfiq. I'm a data scientist at Sophos AI, and this is a summary of our team's research efforts on benchmarking the capabilities of large language models, also known as LLMs, for defensive cybersecurity use cases. We've all been witnessing the recent progress in LLMs, which has been nothing short of remarkable. These powerful models have proven to be effective across a variety of generic tasks, as shown by multiple leaderboards on platforms like Hugging Face. For specialized areas like cybersecurity, where subject matter expertise is key, it gets a bit trickier because it's hard to infer how these models might do on such specialized domains from these generic leaderboards. Here, fine-tuning and knowledge distillation techniques can greatly enhance the effectiveness of LLMs. In our study, we proposed three security-focused benchmark tasks to assess various well-known LLMs and aid in selecting and evaluating the most suitable base model for fine-tuning or distillation for cybersecurity. So for this analysis, here are our chosen LLM contestants. We've picked them from several different organizations, including OpenAI, Mosaic ML, and others. And we have selected them based on different criteria, so number of parameters, context window length, open or closed source, etc. Here you can see a full list of models that we considered for our benchmarking trials. On to our benchmarking tasks. For the first one, we evaluate LLM's ability to convert natural language questions into SQL queries. The goal here is to facilitate information retrieval without extensive technical expertise. This capability can, for example, streamline security analysts' incident investigation processes. We approach this task as a three-shot prompting problem as shown here. First, the model is instructed to translate a request into SQL. Then some schema information is provided so that it knows how the underlying data is, and it can, for example, know which column names to use. Then we provide the three shots, which are three example request answer pairs that are provided as reference to the model for what we want it to do. And then the fourth request is the one we actually want answered, and it's provided at the end here. For this benchmark and using the template of the prompt we've seen, we generate 100 such prompts and collect the target queries and target result sets for them. We then evaluate our contestant model's responses based on three measures. First, we check if the query from the model is an exact match with the expected one. If it is not, then we assess the accuracy of query execution through the comparison of the results against the target. And because this may be prone to false positives and false negatives, we further ask GPT-4 to evaluate the query statement equivalence. And the results we've obtained are presented here, where we can see that GPT-4 is our best performing model as it has the highest accuracy. It's closely followed by Code Llama 34 billion Instruct, and then we have the two Claude models, the V21 and the Instant. The Code Llama performance here makes sense because these models are specifically tuned to produce code. We can see that even the smaller versions, so the 13 billion and 7 billion, are faring quite well here. And now onto our second task, which is about the prediction of incident severity. Here, we provide the models with semi-structured alert data that comes from diverse detectors and makes up an incident. And we ask the models to evaluate the severity of this input given a predefined severity scale. The task's objective here is to gauge models' intrinsic security knowledge. And in this setup, a successful model can help analysts organize their incident queues, as well as focus their efforts first and foremost on the more crucial events. Here's an example prompt for this benchmark. So we're basically instructing the model to look at raw alert data pertaining to one incident and classify it based on the given categories. that are actually thoroughly defined. So we give each one's name and the definition of it. We also ask the model to provide its answer in a predefined format. So we ask it to give it as a dictionary where the key is severity underscore pred and the value is whichever one it picks from these. This is to make it easier for us to process these answers and evaluate them. At the end of this prompt, we provide the actual input alert data here. For this benchmark, we've picked a few thousand severity labeled incidents and used them to evaluate our models. Please note that we have identified some label noise in the severity annotations, and that lowers the ceiling of achievable performance here. Regardless, out of the box, none of the models performed well enough for us to convincingly say they were doing anything better than arbitrary guesswork. We tried different prompting settings from 0-shot to 3-shot with random incidents as well as with nearest neighbors, and none of these experiments crossed the threshold of baseline accuracy. We are showing here one model per experimental setup, and in green we have XGBoost on two features that we've identified as most commonly used by security analysts in their initial assessment of severity. Then in a 0-shot prompting setting, we have Claude V2, that was the best, and in 3-shot we have GPT-4. Our best performing model with nearly 50% accuracy, which is still quite low, is XGBoost with GPT-3 embeddings of the input. As we can see here, this was a benchmark that the models have really struggled with. In this benchmark, we've gotten some unexpected responses at times, where even though in our prompt, if you recall, we really tried to hammer on the format that we want the model to provide the answer in and what values it can use. Yet, in spite of those specifications, the model sometimes did whatever they wanted. For example, it started writing a Python function in one instance to provide its answer. In another example, we can see that the model could not find the answer, and so it says that its prediction is undetermined. And in some cases, the model even just regurgitated as a response some alert data that was from the incident input or added more to it. For our third and final task, we have incident summarization. Here we want to assess the ability of a language model to process raw semi-structured alert data input similar to the previous benchmark, but now we wanted to summarize it in a human-readable, nicely formatted way so that security analysts can kickstart their work based on this summary and description of what's happening, and then they can quickly decide what actions are needed, if any, to resolve the incident on hand. For this benchmark, we provide the models with a detailed prompt outlining what we want them to extract and how the final report should look like. There are different components, starting with a summary and overview in a couple of sentences about what's happening in the incident. Then we ask it to extract specific components like MITRE techniques that are observed, the impacted hosts, the active users, as well as a description of the most important events in the incident, in addition to the extraction of the key artifacts, whether they are file paths or command line invocations. The evaluation of this benchmark, we have 315 incidents for which we have human analyst descriptions as our reference, and we try to evaluate model descriptions on different aspects. For instance, for factuality, we extract all the facts that are found by the models and compare them to make sure that they are factually accurate and relevant. We use the least common subsequence and Levenstein distances for that. For the semantics of the entirety of the descriptions, we also rely on BERT score, the cosine similarity between the GPT-3 embeddings, as well as the Meteor score. And here are the results we've obtained for our models. GPT-4 is the clear winner here, and it scores higher across the board in all metrics. Then we have Claude V2 and GPT 3.5 Turbo as our best performance in the proprietary model space. Then we have Llama 2 70 billion as the best performing open source model. The remaining models like Code Llama 34 billion and others are lagging behind. The question of which model to use for your security application is quite nuanced and involves thinking about a lot of different factors. This video has been an attempt at giving you more information on how to make this decision, as well as more food for thought. On purely performance terms, we noticed that GPT-4 and Claude V2 performed the best across all our benchmarks. Key takeaways here are that large language models are quite good out of the box at threat hunting and information retrieval. They would require some guardrails and hand-holding, but we think that this is a potential application where LLMs can be used out of the box with some careful prompt engineering. In terms of incident summarization, from raw data, we saw that most LLMs did an okay job, but they could definitely be further improved with fine-tuning. Finally, with regards to the evaluation of artifacts and severity prediction, that's a hard problem for pre-trained and publicly available LLMs. This will probably require a more specialized LLM specifically trained on cybersecurity data. And with this, I would like to thank you for watching this video.